Okay, next we will calculate the ripple factor of this inductor filter, L filter or series inductor filter. Ripple factor. Now we know that the output voltage of full wave rectifier is expressed using Fourier series. We did it for the, I think, for the half wave rectifier, while for the full wave rectifier I think we did not calculate the Fourier series, but its shape is almost the same. So the output voltage of full wave rectifier, which is denoted by this V0, which is equal to 2Vm if we do the Fourier transformation by pi, like what we did for the half wave rectifier. It's equal to 2Vm over pi minus 4Vm over 3 pi into cos 2 omega t, and then we have another term minus 4Vm over 15 into cos 4 omega t, and then we have another term minus 4Vm over 35 pi, so here we have pi also, into cos 6 omega t minus so on. Let's suppose this is equation 1. This is the Fourier transformation of output voltage of full wave rectifier. We did same calculation for the half wave rectifier, and we didn't do this calculation for the full wave rectifier, but it's the same. The idea behind calculating the output voltage of full wave rectifier is same as what we did for the half wave rectifier. Now in this equation, this first term, this term represent the DC component. Like here we have both AC and DC. So this first term represents the DC component in this output of this full wave rectifier. So the DC voltage VDC, which we already calculated for the full wave rectifier, its value is 2Vm over pi. Let's say this is equation number 2. And the DC current, which will be equal to the DC voltage across the load resistor RA. So its value will be 2Vm over pi RL. I just put the value of VDC here, which is 2Vm over pi. So it's 2Vm over pi divided by RL. So it's this one. This is equation number 3. Now all other terms in this equation 1, like this term, this term, this term, contain frequency because we have this omega. So here this term is with lowest frequency, its frequency is 2 omega. Here the frequency is 2 omega. Here the frequency is 4 omega. Here the frequency is 6 omega. So all these components contain frequency, so they are the AC component of the output of this full wave rectifier. Because in full wave rectifier we have both AC and DC. So the first term represents the DC, while the rest of the terms they represent this AC component of full wave rectifier. Now these terms, like this term, this term, this term, they are also called harmonics. Here we have cos also, but the frequency is 0, so here we have cos 0 t. The frequency is 0 for half wave for the DC current. So this is the first harmonic, this is the second harmonic, this is the third harmonic, and this is called the fourth harmonic. The first harmonic is frequency, which the frequency value is 0, so this represents the DC voltage, while the rest of the terms they contain frequency, so they represent the AC component. Now inductive reactance is XL, which is omega L. Now the value of this inductive reactance increases with increase in frequency. If frequency increases, then inductive reactance will increases. What it means? It means that if frequency increases, then there will be a large opposition to that frequency, that output signal, AC signal. So it means that as we move from second to third, or from third to fourth, and so on, then the frequency also increases. The frequency increases from 2 omega. The second harmonic is of frequency 2 omega. The third harmonic is of frequency 4 omega. The sixth harmonic is of frequency 6 omega. As the frequency is increasing from terms to term, from this to this, this to this, the frequency increases, so the inductive reactance also increases. Inductive reactance, which is directly proportional to frequency, also increases from second to third and so on. Thus the inductor offers very high resistance, a very high position to component with frequency 4 omega, 6 omega, and so on. We can say that high opposition will be offered by the inductor to the higher harmonics, to these harmonics. So their contribution will be neglected because these terms will not pass through the inductor because their frequency is large, and the corresponding opposition to these frequency will be large. So the inductor will not allow these harmonic through it. Now, while the second harmonic may pass, this harmonic may pass through the inductor because the opposition to this, or the resistance to this harmonic, will be small. So overall, once this output of this rectifier, which is this one, passes through the inductor, then the inductor will allow this DC, because for this the reactance and the resistance is 0. And might be this term may also passes through the inductor, but this term will be blocked. So the output through the rectifier, the output through the rectifier, the inductor filter, when this output passes through the inductor filter, then the output after the inductor filter will be of this type, which is 2Vm over pi minus 4Vm over 3 pi into cos 2 omega t. This is DC component. This will pass surely through the inductor, while this component, this is the AC component. This component, which is the AC component, but its frequency is small, so the resistance to this component, this harmonic, will be small. So this component might pass through the inductor. So the current after the inductor, through the filter. So the current after the output voltage, the voltage after the filter, will be this form. Will be of this form. Now, this is called equation 4. We call it equation number 4. Now, AC component of output voltage. AC component of output voltage. will be VAC, which I represent by VAC, which is 4 Vm over 3 pi into cos 2 omega. Because we already mentioned here that the output of inductor is not a straight line, but there are some variation. So the variations come from this one, because a part of this AC voltage will also flow through the inductor. So the AC component of the output voltage will be this one. So this terms represent this variation. It is not exactly the straight line, but there are some variations. So this terms represent this variation. Now the corresponding AC current will be the corresponding AC current will be IAC, which is the AC voltage divided by the resistance. Now the resistance here is of two types now. One is the resistance offered by the inductor, and the other one is the resistance offered by the what we call it. One is the resistance offered by this load resistance. So their sum is called the resistance of inductor plus the resistance of this resistor. Their sum is called impedance, which we represent by this symbol Z, where Z represent the impedance. This is basically the resistance, and we know that impedance Z has a value which is square of the load resistance plus square of the inductor resistance, and then we have the square root, and it's called impedance. This is from your previous knowledge, because I hope you people know about it from your FSC course. Now I call this is equation number 5, and this is equation number 6. Now for this term here, the frequency is 2 omega. For this term, the inductive reactance XL will be 2 omega L, because instead of frequency omega we put 2 omega. The frequency is 2 omega. Now this is equation number 6. Now using the value of this impedance in equation number, in this equation, and this IAC, this is equation 6, sorry. Using the value of Z in equation 6, we get the AC current, AC component of the current will be equal to, we have VAC, VAC is 4 Vm over 3 pi. So we have this, instead of AC voltage we will put this value, which is 4 Vm over 3 pi, and we have cos 2 omega t, and then we have this Z, and this Z is equal to RL square plus XL square. This is the AC component of the output current. This is equation number 7. Now I will discuss rest of this, the rest of the part of this topic in the next video.